So good morning, good afternoon, and good evening. My name is Andrew Ball from ESA Tech, and on behalf of my co-hosts and presenters today, it's my pleasure to welcome you all to the sixth and final session of our IPPW webinar series. Before moving to today's topic, I'd like to say a few words about IPPW and what we're trying to accomplish with these webinars. So the International Planetary Probe Workshop was founded in 2003. And almost every year since then, we've had a week-long workshop preceded by a weekend short course focused on the exploration of planets with probes, landers, and aerial vehicles for our community of scientists, engineers, and technologists. The workshop has alternated between the US and Europe, and this year would have been held in Monterey, California, but for the intervention of COVID-19. So instead, this year, we've organized a series of 6 webinars 2 weeks apart, most of them timed for the convenience of attendees in the continental US, east across Europe, the westernmost time zones in Russia, and as far as India, where it's now 8:30 in the evening. For the benefit of those unable to participate in person, including those in the Asia-Pacific region, where this is the middle of the night, we're recording each session. Those recordings can be accessed afterwards at the IPPW 2020 website, which is easily located by searching for IPPW 2020, and I believe the one from the last webinar with our Japanese colleagues is now online. So today is our last webinar of this series, and the next major event is due to be IPPW in September 2021. So today the topic is new concepts in lunar and planetary surface exploration, regarding the forthcoming US decadal survey, which is an important step in the advisory structure for US planetary exploration plans, and is also of interest to the wider international community of planetary exploration. So the Planetary Science and Astrobiology Decadal Survey 2023 to 2032, as it's called, will assess key scientific questions in planetary science and astrobiology, identify priority medium and large class missions and other initiatives, and present a comprehensive research strategy for the 2023 to 2032 timeframe. The current decadal survey process having ended 2022, so we're now looking forward to the next phase. They're slightly less than 10 years apart, the decadal surveys. So today we're going to hear from colleagues from JPL, from Johns Hopkins University Applied Physics Lab, and NASA Goddard Space Flight Center on mission concepts for the Moon, Mercury, and Venus. So with that, thank you for attending, and I'll hand over to Jacob Israelovich for some logistical information ahead of the seminars themselves. Thanks.
Thank you, Andrew. I would like to now instruct our audience to please type their questions into the Q&A interface on the right side of the screen. At the end of the talks, I will read some of these questions to our speaker. Additionally, as a special treat this week, we also have some members of their mission study teams to help answer questions, and they will be doing so in writing using that same Q&A interface. And now to introduce our first speaker, we have Kim Ray of JPL. Kim is a program area manager in JPL's Planetary Science Formulation Program Office. His current responsibilities include the Discovery 2019 campaign and multiple NASA studies for the third Planetary Science Decadal Survey.
Yes, hello, good morning, everybody. My name is Kim Ray, as was mentioned, and I'd like to give a brief introduction actually for John Elliott, who's going to give a talk in this series. John Elliott has been with JPL for 21 years. Prior to that, he worked for Bechtel Corporation on terrestrial nuclear power and TRW on aerospace systems. Many of you probably know John. He's got quite a deep and broad base in nuclear power systems as well. Currently, John is a principal engineer in JPL's Mission Concept Systems Development Group as part of what we call our Engineering Science and Science Directorate at JPL. In this role, John leads concept studies for many of our future planetary science and robotic lunar exploration missions. He's also a core member of what we call the A-Team at JPL that occurs before a point design in Team X, and the focus of the A team is to explore brand new concepts and trade alternatives that can result in what we call out-of-the-box approaches to new missions. John has an additional duty as lead architect and system engineer for the office that I am in, the Mission Formulation Office in JPL's Planetary Science Directorate. Now, in this role, John has led NASA's Ice Giants Predecadal Survey Mission Study, as well as the Pluto study that we did for NASA headquarters, and he currently leads JPL's support to Mark Robinson's Intrepid Predecadal study that was recently selected in the NASA Rosa's Call. That's what John's going to be talking about today. So let's welcome John to this IPPW web seminar on new concepts in lunar and planetary exploration.
Thanks, Kim. I'm going to make sure that I get this thing shared right, and we'll get started. Okay. Good. Oops. Okay, thank you. So I'm going to talk today about the Lunar Intrepid Mission Concept Study. As Kim mentioned, it's one of 10 or 11, depending on how you count it, studies that were awarded to the centers to develop for a predecadal survey. As Kim mentioned, the PI for this study is Mark Robinson from Arizona State University. And we have quite a varied team all around the country that's working on this, both on the science and technical side. So let's see. Just an overview of what the mission is. This is a lunar mission that goes to the moon and consists of a 1,800-kilometer trek across the surface of the moon. And its purpose is to investigate the magmatic history of the moon. That's one of those words where you have to make sure you read it right, but it's looking at the history of magmatism on the moon over the last 4 billion years. And the reason that we have this 1,800-kilometer trek is because there is an area of the moon that you can see in the illustration here, if you look at the globe, where 4 billion years of history are actually laid out along a path that is only 1,800 kilometers. And so by taking a single rover and driving along that path over the course of 4 years, as is our mission plan, we'll be able to look at a huge variety of magmatic regions and be able to elucidate things about the history of the moon and the Earth-Moon system and planetary formation that wouldn't be possible in any simpler way. So a lot of people ask, why do you need to go 1,800 kilometers? And it's really, you know, why do you need to go? I mean, how can you get away with only going 1,800 kilometers? And it just works out with this region of the moon that you can see here. So just going over the mission quickly, we land in the lower left portion of the map there in Reiner Gamma, which is an area that's interesting all by itself. This is an area that has an anomalous magnetic field, and you can see the lightening of the region there, which is thought to be because of diversion of solar wind because of the magnetic field that causes differential aging. So we're going to start there, look at the magnetic field there and the impact on solar wind and cosmic rays. We drive up through the Marias Hills region, which is the second region that's shown on the map there. It's about 2.5 to 3 billion years old. That has very interesting volcanic features in it. It has cinder cones and remnants of volcanism from billions of years ago. We continue up through the Oceanus Prosolarum region, which is also interesting from a magmatic standpoint. It's significantly younger. You're getting into 2 billion to 1 billion years old. And an extra feature of that region is that it is covered and will allow us to drive across rays from Aristarchus crater, which is the next area that we'll be going to. Aristarchus crater is a very young crater, and it has, as a result of the impact that caused that crater, there are rays that expand from it, and they don't show up very well in this picture, but in other pictures you can see them. And by driving across them, we'll actually be able to look at material from deep inside the crater that was blown out during the impact that caused it. So we drive across those, we go to the Aristarchus Plateau, which is a large pyroclastic deposit and is of questionable age. So this is going to be a way to actually figure out how old that region is. It may be in the 2 to 3 billion years old. And then we go to Aristarchus crater, which is thought to be 100 to 200 million years old. So the youngest region that we'll be looking at there. And Aristarchus crater is very interesting on its own. It's a very young crater, and it's got terracing that's visible in it. So it's about 4 kilometers deep, I believe, and so we'll be able to look at that terracing all the way down. We don't actually go into the crater, but from the rim as we drive around, we'll be able to take measurements. And then finally, we end up at the irregular mare patch, which is up in the very top right corner there, which is by its nature, and it's a bit unknown. We've never visited an area like this, and so there's a question mark next to the date, whether it's a 0.1 billion years old or whether it's much more than that. So anyway, by this trek over 4 years, and as I mentioned, it's actually a 3-year baseline mission with a 1-year margin on the end of it. We'll be able to basically answer questions on the evolution of the lunar interior, certainly get a huge amount of information on the diversity of the styles of magnetism, and also be able to evaluate post and placement modifications that have taken place over the evolution of the moon. So the concept of operations at a little bit of a lower scale is that we have a mission that drives during the day, and the lunar day, of course, is 14 days, the night's 14 days roughly. We drive during the day at average speeds of about ½ kilometer per hour. We have a rover design that is designed to go a maximum of 1 kilometer per hour, but because of varying terrain, our average is about half a kilometer per hour. We drive in spurts of 5 hours, where we drive 4 hours and stop for a 1-hour minor science stop to take panoramas and do measurements with our APXS instrument that's placed on the ground on an arm. And then we are going between major investigation sites, which are all plotted out on that path that you saw on the previous slide. Those drives can be 10 kilometers or so, 10 to 15 kilometers between major sites, with these minor sites in between. The stops are all pre-planned. The science sites are pre-planned. We stop at the major sites and employ all of our range of instruments, depending on what the site is, to evaluate the geology and magmatic features of that site. While we're driving, we have 2 or 3 instruments that continuously take measurements. We have a gamma ray neutron spectrometer and an ARMOS instrument that does cosmic radiation measurements and electrostatic monitoring, and also a magnetometer that are kept on all the time as we drive. So we get a continuous map of scientific information while we're driving, and then more detailed investigations in each stop. During the night, and this is critical to one of the trades that we'll be talking about soon, during the night we actually don't drive for distance, but we do drive. That's why we've baselined a radioisotope-powered rover. We stop at the night in an area that we have previously mapped, and we take long-term, long-duration iterations on some of our instruments in that area. Then we move from one place to another at a low speed using earthshine to allow us to drive at night. So that's why we go at a very low speed, and we basically just go between a few spots within a kilometer or 2 and take these long-duration iterations overnight. If we were to use, I'll get to this later, but if we were to use a solar-powered rover, which we've also developed, we could do the same science, but it would take significantly longer because of the restrictions that we would have on taking these measurements at night. So by being able to take them at night, we're able to fit the entire mission into the nominal 3-year period. We have continuous telecom while we're driving and while we're stationary. We have an Omni antenna on the rover, and it allows us to communicate with either a near-Earth network station, which we do 16 hours a day, or a DSN. We've planned one 8-hour DSN pass per day we get fairly high data rate from the DSN and a reduced data rate through the NEN. But we do have continuous monitoring and continuous communication, direct to Earth, of course. The mission design, just to summarize, there are 131 of these major stops that are plotted on the path that you saw on the previous slide, and 981 minor sites over the 3 years. So the instrument suite, I'll just go over this quickly. We have a suite of about 9 instruments, and those include the ARMOS, which is a galactic and cosmic ray instrument that's mounted on the body of the rover, magnetometer, which is mounted on a boom, and of course that'll help us characterize the Reiner gamma area. Gamma ray neutron spectrometer, which is mounted on the belly of the rover, that is one of the instruments that's on pretty much all the time, looking for elemental abundance along the path that we're driving. The TriCam, which is a stereo camera combined with a far cam, a telescopic camera. And the stereo camera is also hooked to a point spectrometer through a fiber optic link. We have on the arm, we have a robot arm, a 5 degree of freedom robot arm that has an APXS, an alpha particle X-ray spectrometer on it that we use to put down on the regolith to measure materials on the elemental abundance in the regolith, or interesting rocks that we might come by. The arm is flexible enough to basically measure whatever we want to there. So that's on the arm. We also have a hand lens imager on the arm to take context imagery of where we're measuring. Then we have an electrostatic analyzer, which is also continuously on and measures the solar wind. And finally, a laser retroreflector, which is a passive instrument that's would be used with an orbiter if an orbiter wanted to take measurements as we drive or once we're stationary. Delivery assumptions. I know this is the IPPW. We like to talk about descent and landing. In this case, our descent and landing has been provided to us by the commercial lunar payload system or services. We've been in discussions with NASA, and in this time frame, the best way to get to the moon for a rover like this will be CLIPS. And I note that the Viper rover has just been awarded a contract with Astrobotic for landing their rover, and their rover is very much in the same class as our rover as far as size and mass goes. And so we are using that as an example of the sort of service that we would use to get to the moon. So you won't see much on landing in this presentation. We focused mostly on the rover. So in looking at a rover like this, you can see from the table that's at the bottom of this chart that we're talking about performance that's significantly higher than anything that's been flown to the moon in the past. And it's good to look at what has been flown to the moon. We've got 2 of the Soviet Lunokhod rovers that were operated for various periods of time, up to 10 months for Lunokhod 1 on the moon, and drove pretty significant distances of 10 kilometers for Lunokhod 1 and 39 kilometers for Lunokhod 2. And then, of course, the Apollo lunar roving vehicles that were driven by the astronauts, which went quite a distance in a very short period of time. They were significantly faster, as you can see, than the other rovers that we have here, but they didn't have to last very long either. We also have the 2 Chinese rovers, the U-2 and U-2-2, which are more short-range rovers, but significantly long-lived. And it's interesting to note on the U-2 that its mission duration was actually 31 months on the surface of the moon. It survived for quite a while, but its mobility system failed after 2 months, which is why you see a little bit of a discrepancy in the summary, between the summary and the mission duration there. Intrepid, on the other hand, needs to go 1,800 kilometers and do that in 48 months. The speed that Intrepid goes is not out of class with some of these others, at least Lunokhod 2, which actually went twice as fast, and of course the Apollo LRV, which went significantly faster. And the duration is not outside of the realm of rovers. Certainly the Mars rovers that we've put up have lasted significantly longer than 48 months. But the distance that it needs to drive, combined with the environment on the moon, things like and the terrain that it has to go over on the moon, combined to make some very major rover trades related to mobility and autonomy, as well as the power source. So the mobility trade we'll talk about in the next chart in more detail, but this was something where we needed to look at what sort of mobility systems were available to us, what has the heritage, what has the testing, what has the longevity to be able to operate in these conditions for this period of time. And autonomy actually became a very critical trade because, again, as you see, it's quite an involved mission with a lot of stops, a lot of driving, and a fairly constrained schedule to do all this in. And so there was a significant discussion, as you'll see in the next chart, or in a couple of charts, about how to implement this. And then finally, the power source. We talked about the power source. I alluded to it a little bit earlier. We looked at both a solar-powered version of the rover and an RPS-powered, RPS is radioisotope-powered version of the rover. And the benefit of the RPS version is, as I mentioned before, that it can actually drive at night, take measurements at night, and actually communicate at night as well. Whereas the solar-powered rover, because of the restrictions, because of the very long lunar night that it has to survive through, relies on batteries overnight. And to keep the battery size manageable, it essentially shuts down and maintains itself in survival mode overnight. And so you lose that ability to take significant science and the ability to move. So we developed both designs, and you'll see both of them in here, and both appear to be feasible. If we were to use the solar design, it could do the science, but it's been determined that it would probably just about double the mission length. And so the baseline right now is using an RTG, and in fact, it's using a next-gen RTG, which was allowed by the ground rules, is the next generation of radioisotope power systems that will be coming out and should be available by about 2030. And the one that we're using in this case is a 300-watt 12 GPHS version of that. So mobility trades, let me just go over a little bit of this. The key drivers we looked at were robustness and durability, of course, given the mission requirements. Also energy efficiency. We wanted to try to keep this to as low power as possible, and the ability to handle the terrain. The good thing is we have a very good idea of what terrain we're up against here. We have excellent coverage by LRO of the whole path that we're driving on, and so we have a good feel for what the hazards are. And it's actually much more benign, for instance, than driving on Mars. Fewer rocks. It's not as, it doesn't have the same slip characteristics and things like that. So we have the constraints that you see down there. We constrained it to a 15-degree max slope. We have a rock distribution that we've determined to be about 10% on the crater rims at the worst. And when I say rock distribution, I mean rocks that would be that we would have to actually drive over rather than driving around. Sorry, would have to drive around rather than being able to drive over. About 10% along the crater rim, which will cause us to make sure that our path avoids those, but it's only about 1% in other places of the traverse. So we did trades on wheeled versus tracked at first. I've always liked tracked rovers, but nobody else seems to. So they actually are not a very good application for a lunar or a Mars rover, it turns out, especially when you need when you don't have access to maintenance. For the configuration, we looked at a variety of different ways of setting up the wheels and how many wheels we would have. We determined that in the end that the 4-wheel configuration is actually the most versatile for this. Like the Apollo LRV, it allows us to put large wheels on, and this ties into the wheel trade that we have down towards the bottom. Large wheels give us a lot of benefits. They allow us to go over rocks easier. They are good for energy efficiency, and they also allow us to gear the wheels to the point where we can keep the motors within their qualified number of turns over the course of this mission. So we thought this was a good choice. 4 wheels, large wheels, And just jumping down to the wheels section, already we adopted the compliant mesh wheel design, very similar to what was used on the Apollo lunar rover, and has been improved lately by the Glenn Research Center. They've been doing a lot of work on wheels like this. So the robustness of these has been seen to be superior for the sort of traction, for the sort of trafficability requirements that we have for the moon for this mission. And then we also looked at how we would do the suspension, and we ended up with the simplest being a front rocker suspension. And you'll see that in a video that I've got on the next chart that just sort of shows how this rover would drive. And hopefully this comes through okay on the WebEx. It's always a little iffy with videos on WebEx, but you can see the front rocker on the front of the rover. This is driving over a simulated moon surface, which is actually based on real terrain maps. So just gives you an idea. The front rocker allows all four wheels basically to stay on the ground in almost any condition, and it basically gives you the simplest implementation. The wheels are also four-wheel, they're four-wheel drive, they're also four-wheel steered, so it allows us to actually drive sideways if such a situation ever came up that we needed to. So moving on to autonomy trades, we had to look at what we could do for autonomy, and we started out saying, could we just drive it joystick like they did the Lunacods? And we didn't think for a mission this long that that would be a good choice. We looked at ground control, ground decide, ground compute, onboard decide, etc. And it was determined that given the amount of distance we have to travel and the fact that we have to drive 24 hours a day, basically during the daylight hours and somewhat during the night as well, the only way to make this work was onboard autonomy. So we have onboard decide autonomy in there. We've used for sensor suites, we have cameras and a sun sensor, and we use for localization, we're using crater recognition, so terrain recognition combined with the sun sensor, and our IMU tells us basically what heading we're on and where we are, so we use that for localization. For sensors internally, we have the IMUs, we have Hall sensors, Hall effect sensors on the wheels, and that was driven by the thermal requirements because they can stand the heat during the day. Then for compute, we're using some new developments from JPL, Sabertooth computer system, which uses a Leon 4 processor, and we're also using the Vertex 5 for some of the autonomous driving. Okay, thermal design. I wanted to talk about this because this is another critical thing for any lunar mission that has to survive during the day and the night. We have very high daytime temperatures, and in that situation you have to get heat out of the rover, and so we have a large radiator on the top of the rover, and we have it connected through advanced thermal switches so that it can be disconnected at night, because at night you have to keep all that heat in, obviously. So for the RTG option, this is less of an issue because the RTG is always putting out, I think in this case, 3,000 watts of waste heat. We've got plenty of heat to survive overnight, but for the solar version, it's quite a complicated, or it's quite an important design feature that we build a warm electronics box with these high turn down thermal switches. So it gives you an illustration of how it works there. And basically the thermal switches allow you to completely disconnect from the radiator system at night and keep all your heat in. So in this way, we've basically been able to keep the heat loss down to about 10 watts overnight. So we're supplying 20 watts total to the rover to survive overnight, and that leads us to need about 120, 130 kilograms of lithium-ion batteries for overnight survival. So let's see what they actually look like. This is the RTG-powered rover concept. It's about 2.5 meters long and about 2 meters wide. It uses a 12 GPHS next-gen RTG mounted on the rear, as you can see, which gives it easy access for assembly at the Cape. It's got a lifetime of greater than 4 years. I think most of these we've gone over. The ground clearance is 60 centimeters. The wheel diameter is 80 centimeters. It says 4 degree of freedom robotic arm. I'm sorry about that. That's actually 5. And its mass is, it came out to be 420, sorry, my screen has stuff over it, so I got to get the number right. 423 kilograms, carrying about 20 kilograms of science payload. It's an interesting design in that you can see it has a spoiler on the back, and a lot of people ask what that is. That's actually a mount for rear-facing cameras. So another feature of the mobility system, oh, that's up here. I don't know if you can see my pointer. Another feature of the mobility system is that the rover can drive backwards or forwards equally well. It has a set of navigation cameras on both ends. Let's go to the next chart. Oh, and another interesting feature here, these are not actually fenders. These wheel thermal shields that are down there are thermal shields for the to keep the heat of the RTG from overheating the wheel motors. But they look like fenders, and I kind of like that. This is the solar-powered rover concept. It's very similar inside. It's mostly the same. The structure is significantly different because of the thermal design that you saw in the earlier chart. It is designed only for operation in the daytime with survival overnight and limited science data taking. It does have 20 watts of heater power that it needs to use overnight that can be used in science instruments instead. So we have the ability to take some measurements overnight, but generally it's in a survival mode. The mass of this is significantly higher. It's 564 kilograms. And again, that's largely because of that 130 kilograms of battery that it carries to survive overnight. But the other performance features are about the same. And this picture also shows you the location of the instruments that we mentioned before. And I'm going to go through this quickly because I see my time is almost up. The mass estimates just gives you an idea. You can see the power for the solar option is what dominates that at 192 kilograms for the entire power subsystem. And then power modes. The way we have designed this, we have significant power margins in all modes. The end of mission output of the RTG that we're using is 274 watts. And you can see that the highest power mode is traverse daytime. So when we're driving during the day, we need 231 watts. So we have significant margin in all these areas. We don't need to stop and recharge the batteries periodically. We actually looked at a case where that, we looked at using an RTG where that would be the case. And the problem again with this rapid pace of operations is that you just don't have time to do that. So by going to this RTG with this power output, we have a system that can operate continuously and easily fulfill the objectives within the allotted time. All right, I think that's the last, and so I'd like to thank you all and see if there are any questions.
Thank you, John. As a reminder to our audience, please type your questions into the Q&A interface on your right. I think we have time for 1 or 2 questions. To start us off, we've prepared a few of these ahead of time. So John, so Lunar 2, failed when it drove into a crater. So I was curious, does Intrepid include any fault avoidance or fault recovery capabilities that would reduce the risk of an accident, or if one occurs, some method of extricating it?
Yes, absolutely. There are several layers to that, and fault protection and fault recovery is something that we've been working very hard lately. The first thing is the way the autonomous driving system works. It sees where it's driving and it chooses where it's going to go. Well, actually, the first thing is the fact that we have these detailed terrain maps, and we also have the detailed overhead maps, so we can actually see any hazard that's something on the order of a meter or less and avoid that by choosing our route, which is something that Lunar didn't have at the time. We didn't have maps of that quality back then. And then we have the onboard sensing system that will be able to avoid hazards. Rocks are pretty easy. The smaller craters sometimes can be hard to see, and we've designed the rover to be able to handle those craters. And then if it does get into a bad situation, we have the ability, because of the mobility design, we have the ability to either back out of that situation, or because the wheels can turn, all the way around and go sideways, we have the ability to go sideways to get out of bad situations, to back away from hitting a rock or something like that. We don't have the problem that LunaCod had of having a solar array that stuck out the way it did. Our configuration doesn't really shouldn't get us into problems like that. But yes, we're definitely working on fault avoidance, fault recovery, and hope to have that taken care of.
So we have one question here from Jeff Landis. The list of rovers would be more useful if it also included the Mars rovers. Opportunity in particular has made one long drive, although not as long as proposed here. It's probably the best current example of a dedicated goal-oriented traverse. Can you comment a bit on that, John?
Yes, yeah, you're right. I mean, this was just, this particular table, we just wanted to show the lunar rovers, but the Mars rovers, of course, were a huge inspiration for our design in many ways. And in fact, the autonomy system that we're using is really just, is really a development of the autonomy system that's already on board on MSL. And Mars 2020 has an upgraded system of that, for that. So we are definitely building on the legacy that's coming to us from the Mars rovers, and the same folks, a lot of the same folks that worked on those worked on the design for this as well.
Okay, thanks, John. So I think in the interest of time, we'll move on to the next speaker. We have Steve Arnold to introduce our next speaker. Steve is the Deputy Head of the Civil Space at the Johns Hopkins Applied Physics Lab. Steve.
Yeah, thank you, Jacob. Hopefully you can hear me and see me well. By the way, I wanted to thank Jim, Andrew, and you, Jacob, for going to the effort of hosting this session virtually. You know, I think all of our lives have been very disrupted lately, but it's important for our community to get together. And what's interesting, actually, is that a lot of these concepts, all of them, have been developed in kind of a remote environment where we had to, come up with mission design lab concepts working in various locations, spread out, our staff spread out across sometimes even the nation. So it's, as we're hearing from these very effective presentations today, it sounds like it's gone actually pretty well. And we certainly, as an institution, have some lessons learned in that. But so just wanted to start off by thanking you for hosting this. At APL, we're obviously very committed to the decadal process as the nation tries to prioritize and get ready for the next decadal. That's something that we want to continue to participate and help lead there. For this pre-decadal mission concept study that NASA put out, a call to the community, they had a really good response. They had over 50 concepts that came in, and you're hearing from 3 of them today, and they ultimately selected about 10 of them to invest some money into to develop them. APL has a very large footprint on that. We're leading one related to Neptune Triton with PI Abby Reimer. We have another one for Enceladus with Shannon McKenzie, and helping with the mission design lab with a Pluto orbiter. But today we're going to talk about the Mercury lander concept. And so with that, I wanted to introduce Sinai Kubota, who is the lead for APL in the system engineering design for this concept. So it's a very exciting concept, the Mercury lander. Everyone knows about the very intensive environment there, and so we'll be walking through that. But Sinai is a systems engineer, and she works in our advanced concepts group here at the lab. She's also the deputy spacecraft engineer for our Parker Solar Probe mission, which you might have heard of. She's helping to lead and design all of the fault management there, and took it really from cradle to grave, from very beginning of the concept development all the way through operations. That design has held up remarkably well for Parker Solar Probe, and it continues to fly through this very intense environment of the sun's corona. So she's taken that experience and now leveraging that and leading new mission concept development here at the lab for APL. So Sinai, I wanted to turn it over to you to talk about the Mercury lander mission concept, please.
Thanks, Dave. All right, gonna get set up to share my screen and take myself off of it so you can just look at my slides. All right. Hopefully that is working well.
We can see it. Yes, looks good.
Okay. Thank you. All right. So yeah, I'm going to talk about the Mercury lander concept. Here is a quick look at what I'll be talking about today. The scope requested of this presentation was to focus on the technical challenges of landing on Mercury. The details of the science objectives, the instrument payload, and operations were covered by our PI, Carolyn Ernst, during her presentation for the LPSC workshop in May, and of course will also be covered in our report, which will be publicly available, and I hope everybody reads it. So for this presentation, I'm going to set the stage with a little bit of the history and current happenings in the realm of Mercury exploration, and then talk about our mission concept, the challenges of a Mercury lander mission and how we met them. So the history here. So NASA had the Mariner 10 mission back in the 70s, in the mid-70s, and that one did 3 flybys of Mercury in 74 and 75. There was also another NASA mission that is near and dear to our hearts at APL. The Messenger mission launched in 2004, also did 3 flybys, and then had an orbital campaign from 2011 to 2015. Then there's BepiColombo, that's on its way now. We're all very excited about that. It launched in 2018, which it turns out is no longer last year. Time flies. So it is on its way. It's going to do several flybys of Mercury beginning next year and going through 2025 when it starts its orbital campaign. And so it'll be doing orbital reconnaissance from 2025 to 2028. So in advancing planetary exploration, there are typically 3 key steps highlighted. Mariner 10 and Messenger have done flybys, and BepiColombo soon will too. Messenger had an extended orbital campaign at Mercury, and BepiColombo soon will too, but we haven't landed yet. The Mercury lander, there was a Mercury lander mission concept study performed in 2010 for the previous decadal survey. Key challenges that they highlighted were the launch energy and delta V required for the mission. They explored a variety of permutations of the design with low thrust and ballistic trajectories and both reduced and robust payloads, so different lander size options. All were found to be well outside the New Frontiers cost cap. One of the recommendations made by that study to enable missions like this in the future was the qualification of higher energy launch vehicle configurations. And thankfully for our study, that did happen. So that study, the 2010 one, was conducted prior to Messenger's orbital campaign. And following that campaign, the science case for a landed mission was even further strengthened by the unexpected findings from the Messenger mission. So this, the past decadal survey recognized the importance of a landed mission to Mercury, and what they concluded was, given all the advances that will likely come from Messenger and BepiColombo, as well as ongoing technology and capability enhancement work, the high priority of Mercury landed science could be revisited at the earliest opportunity, mid to late in this decade. So that's what we're doing. So a lot has happened in the last decade. Thankfully, we do now have expanded launch vehicle options and higher performance capability. The development of solar electric propulsion systems has continued to advance. For this study, we evaluated several systems. We found that NEXT-C is the best fit. It gives us the thrust we need while minimizing the propellant that we need to use. And the DART spacecraft is launching next year and will be flying NEXT-C. The radioisotope power system development has had a bit of a rocky road. The 2010 study included an ASRG, but in the development since then, the next-gen RTG is now being developed and offers considerably higher power, which is great for us. So we are very much leveraging the technology development of the past decade to enable this mission. There's also a difference in the costing guidelines. Both our study and the 2010 one were evaluating New Frontiers feasibility, and the change now is that the cost cap excludes the launch vehicle costs and costs of phases ENF operations. Okay, so the edict. The edict that was selected for further study, the proposal that our PI Carolyn put forth, was to establish if a Mercury lander mission is feasible as a New Frontiers class mission. The finding is yes. So hopefully we can put a final check mark next to that land line in the list. So why land on Mercury? Mercury holds unique clues about the original distribution of elements in the earliest stages of solar system development, and about how planets and exoplanets form and evolve in close proximity to their host stars. Messenger revealed that Mercury is unique among terrestrial planets and doesn't match any of the predictions previously put forth about the planet's origin. It also reiterated that we need in situ measurements from the surface to understand it. The science goals achieved by this design concept are ambitious and comprehensive, including the investigations of geochemistry, geophysics, the Mercury environment, and characterization of the geology. So our mission concept design overview. We are a 4-stage flight system design that delivers that comprehensive science payload suite to the Mercury surface for an 88 Earth day, which is one full Mercury year landed science campaign. I'll talk more about much of what's shown here on this slide in the upcoming slides, and it'll be in context then. So I'm just going to move quickly through this one here and hit the highlights. So we have a solar electric propulsion cruise stage. It takes us on our 10-year trajectory, launches, well, it, with the rest of the stack, launches on an expendable Falcon Heavy. We go through 1 Earth, 2 Venus, and 5 Mercury gravity assists. And then after we orbit match with Mercury, we jettison the cruise stage. We have a bicrop orbital stage, and we jettison that prior to the braking burn. We have a solid rocket motor descent stage that takes out 3.4 kilometers per second of velocity because it's going to an airless high gravity planet. Then we have a bicrop lander to do the final soft landing with hazard detection and avoidance. So with Delta V being one of the biggest challenges, we have propulsion systems stacked on top of propulsion systems and a system fuel mass fraction of about 60%. So the goal is to land and operate the best payload. Here I have listed the half-dozen key challenges that distinguish a Mercury lander mission. They are large delta V requirement to reach Mercury, the large delta V requirement to orbit Mercury, and the large delta V requirement to land on Mercury. Then there's the extreme thermal environment around Mercury, the extreme thermal environment on Mercury, and the limited surface characterization that we have of the planet. So the fun thing about the Mercury lander challenges is they compound, and this starts with what it takes to land. Like the moon, there's no atmosphere to assist with the slowdown for a graceful landing. And then on top of that, Mercury's gravity is more than double that of the moon. So that's a lot of energy to remove. And of course, the larger the propulsion system, the larger the vehicle mass, the larger the vehicle mass, the larger the prop system requirements, and this is the start of the compounding. It's a basic problem, but it has a big impact for landing on Mercury. Went too far, going back. So where we are right now, we selected a solid rocket motor. Well, where we are right now in the slides. We selected a solid rocket motor and bicop combined system for landing to optimize mass efficiency. Because the size of the lander and the descent system drives the system design for the orbit phase. Where there are also large delta V requirements for the orbit insertion burn and orbit lowering maneuvers. So minimizing system mass in the orbital phase is important because it impacts the system design for the cruise phase. Again, all of these are compounding. Any mass we have to use to land, we have to carry in orbit. Any mass we have to carry in orbit, we have to carry in cruise. For the cruise phase, we did trade ballistic and low thrust trajectories, but fuel requirements for a ballistic trajectory are just not feasible. So we selected the low thrust approach. Doing so requires about 9 kilowatts of power to support the solar electric propulsion, and the solar arrays that provide that power need to be sized to accommodate that, plus the solar cell degradation through the 10-year cruise. And with the increasingly extreme thermal environment as the system approaches Mercury, the solar array wings need to be rotated off-sun to minimize the cell temperature. The array needs to be sized to still be able to supply the power needed when rotated off-sun. So this makes for large solar arrays, and as true with any mass growth, and noted earlier, a large propulsion system to meet the delta V requirements. So to recap where we are now, we have landing accomplished with a solid rocket motor and biprop system, and cruise with SEP. Now to consider how to handle the orbit insertion, station keeping, and orbit lowering. The quote-unquote traditional approach to this problem is a 3-stage system, and we looked into using the cruise SEP system for the orbit phase. But even at the highest power settings, using SEP would turn the orbit phase into several years. It would stretch it out into years. And then remember the exacerbation of solar array growth with degradation over time and temperature. So we chose to use a biprop system for orbiting. If we had a 3-stage system, we'd still need to bring that cruise SEP system into orbit. And that's a big vehicle to carry through the large delta V requirements of the orbit insertion burn and for orbit lowering. But since we chose the biprop implementation for the orbit phase, we don't need to bring the SEP system into orbit. So we chose to move to a 4-stage system and jettison the cruise stage before MOI. So to recap, we meet the large delta V requirements for cruise with a system that has prioritized mass efficiency for all phases and with a solar electric propulsion cruise stage. We minimize the amount we let the thermal environment around Mercury exacerbate large delta V requirements to orbit the planet, and we meet those delta V requirements by jettisoning the cruise stage before MOI and using a biprop stage for the orbital phase. And we meet the large delta V requirement for landing by using the orbital stage to lower the system to an orbit that minimizes the landing delta V requirement, then jettisoning the orbital stage before the braking burn, using an SRM for the braking burn, jettisoning it after burnout, and using a biprop lander for the final landing. And then we land and operate the best payload. All right, more about that extreme thermal environment around Mercury. So early on, we did look into doing a dedicated orbital campaign for landing site imaging to buy down the safe landing risk. But thermal constraints of low orbits quickly moved that off the table. Mercury sees up to 11 times the solar radiation that we see here on Earth. So our design includes sunshades like those that were successfully implemented on Messenger to protect each stage from the sun. Even with that though, the spacecraft sometimes passes in between the sun and the illuminated planet, which exposes the vehicle to the hot Mercury surface. So these are some of the challenges, and we did a comprehensive trade study to select an orbit that is thermally safe for the whole system, including the solid rocket motor that we're carrying and the RTG. And that's at 100 kilometers by 6,000 kilometers. This analysis also informed when the vehicle would be safe to begin lowering its orbit to set up for descent, and that we've constrained to be after the Mercury true anomaly of 130 degrees. So there's also the extreme thermal environment on Mercury. Being the innermost planet, daytime temperatures get very toasty, and it's just way too hot during the day to support either solar array or RTG as power sources. Landing at dusk or low sun elevations keeps the surface temperatures at manageable levels. Even with that though, we need to land with the lander between the RTG and the sun to keep the RTG in shadow. But this still gives us a landed operational life of a full Mercury year, which is substantial. Okay, surface characterization of Mercury. The highest resolution images we have from MESSENGER are about 2 meter per pixel, and those are from a small number of spots in the northern hemisphere. In the southern hemisphere, which is the target area for our particular concept study, the resolution is about 100 meters per pixel. BepiColombo is on its way and will begin its orbital campaign in 2025. About a year later, it will be positioned well for observations of our baseline landing site for this study. And it's going to be able to do a lot of great work to characterize the area. Unfortunately, it still won't be able to get the resolution we need to identify hazards at a sub-meter scale. But detailed mapping and modeling studies can be performed using the MESSENGER and BepiColombo data that's available to constrain the size of objects in the range that can be seen, and then extrapolate it to lower sizes. Monte Carlo analysis can then be performed using that modeled size distribution to determine a probability of safe landing, and then that would inform the size of the area that the vehicle has to be capable of traversing during hazard avoidance. The other note is Apollo landing sites may be a useful analog. For this study, we are targeting Mercury's intercrater plains, and they are thought to resemble the Apollo 17 site. To supplement the analysis that will be done based on the MESSENGER and BepiColombo data, we included an LROC-like narrow-angle camera on the orbital stage. That can provide about 1 meter pixel scale imaging of the landing area from the 100-kilometer altitude. That imaging can then be used for a final down selection of the target landing zone. Then we depend on the scanning LiDAR, which will produce a hazard map during the coast arc, which is after solid rocket motor burnout and before the final liquid descent begins. Performance estimates at that first point at about 3-kilometer altitude vary from about 0.5 meter per pixel to better than 1/10 of a meter. That depends on the sampling rate chosen for the LiDAR. And of course, the hazard map continues to be refined with increasing resolution on descent. So that's what I have for our design concept. There are a few questions that are frequently asked, so I thought I'd just go ahead and address them here. So some of those questions are, did the study consider a comm relay? And fair question, well, the design does include an orbital stage that we jettison. Using it as a comm relay during the landed science campaign is just not feasible while meeting that overarching goal of optimizing landed science within a New Frontiers class mission scope. We have consolidated our flight system command and data handling to the lander to facilitate system mass savings and prioritize the landed mass. Maintaining the orbital stage would also require additional propellants to return the vehicle to a thermally safe orbit and for station keeping, further exacerbating the stage growth and reducing the landed mass. Another question we get is, what about mobility? But kind of like the comm relay, we didn't consider a rover because doing so would run counter to that overarching goal. The additional mass that would be needed to accommodate mobility would force a smaller payload fleet and reduce the breadth of science data that we'd be able to collect. As far as daytime operations, I touched on this a little bit during the presentation, but RTG and solar array implementations are just not feasible in Mercury daytime temperatures, even at high latitudes if they see direct sunlight. And a battery-powered implementation would severely limit the operational lifetime and reduce the science data collection. That's what I have. So I guess I'll stop sharing and pass it back to Jacob.
Excellent. Thanks, Sanai, for the presentation. As a reminder to our audience, please type your questions into the Q&A panel on your right. So I'll start us off with another prepared question here. ESA considered a lander, but it would have landed close to the poles where the temperature extremes are smaller. Was a polar lander considered as part of your study?
So our study is intended to demonstrate the feasibility of a Mercury lander altogether. The science team selected the landing area of interest for the study, and they believe it's scientifically important. But they also believe that landing anywhere on the planet is scientifically important. Whether or not the temperature extremes are smaller at the poles did not impact our study. Even with the smaller temperature extremes, any direct sunlight is pretty prohibitive for RTGs and solar rays. And the landed lifespan we could have with the batteries is short.
Okay, thank you. So here's another prepared question. ESA's Bepi-Colombo orbiter will be in a circular orbit, and will produce a much more detailed map of the entire planet than what was possible with Messenger. What impact do you expect that to have on the landing site selection?
So again, unfortunately, even with that more detailed map, it still won't have the resolution that we need to be able to use that data directly. But it will absolutely help in the modeling and analysis efforts.
Okay. Here's another question. The northern regions of Mercury contain frozen volatiles and permanently shattered regions. Was there any consideration of visiting these areas, and what types of technology would you need to access these types of frozen volatiles?
So we didn't look into going to a PSR for this study, and I think that would be something that would be really interesting to the science community. But again, the main objective for this study was to find out if we can land a vehicle on Mercury with a New Frontiers budget. We've done that, and we hope that the community takes this input and that it drives more discussion on where they'd like to go. Going to a PSR isn't easy, but a Mercury PSR mission could probably leverage the work that's being done to get to lunar PSRs.
Okay. Here's a follow-up question from Alex Hoffman. Are there areas of the poles that are in shadow year-round, which could extend the life of the lander?
There are. The trade-off that could be examined when this is considered for future development is permanently shadowed regions and craters also don't have the calm visibility necessarily that other areas have. So that line of sight is really helpful for us as well. But yeah, certainly there are a whole lot of options that can be considered for Mercury landers, and we look forward to seeing them.
Okay, great. Thanks, Sanai. I think let's move on to our next speaker, if that's okay. We have Michael Amato to introduce our third and final speaker for today. Michael is the NASA Goddard Planetary Line of Business Manager and Lead Engineer for NASA Goddard. Take it away, Michael.
Thank you, Jacob. Appreciate everybody joining us here today. Something I think that Kim and Steve both mentioned, but bears repeating, is that these decadal studies that we're summarizing a few of here are pretty important to us. They set the stage for the decadal discussions and panels, which then set the stage for many of us for the next decades worth of work. They also happen to be pretty interesting to work on. They can be exciting because these studies are an awful lot about what is really possible in the next decade. And that's the thing to work on and useful for the next set of discussions for priorities, at least in the U.S. Here at Goddard, we're doing 3 of the studies. One of them is a lunar geophysical network. Many of you will recognize that from previous studies and incarnations. This one has a few new wrinkles. It's focusing on seismology and heat flow from multiple locations on the moon, and that's a pretty exciting mission. It has a flavor of it that's trying to find how much of that mission can fit in New Frontiers. We're also doing the geochronology mission. That's really 3 missions. The lunar geochronology mission is multiple sites trying to age date samples. Many of you may recognize that as a pretty significant challenge in the science world. Trying to get accurate age dates for various samples from various locations is one of the few ways we're going to solve some of the formation and history questions at targets, including the moon. We're also doing a version of that for Vesta at 2 sites, and a single site lander for Mars, also geochronology, which is outside of sample return, and even with sample return from one location is a big challenge for getting the age questions answered in multiple cases. But today, you're going to hear about the Venus flagship mission. It's a broad mission, an exciting mission to do that. There's a lot still to do at Venus. And to talk about that, we're going to have one of our systems engineers, Richard Lynch. He's been at Goddard as a contractor and civil service mission system engineer for 20 years. We had a discussion about how many years he'd actually been here. We came down to 20. He should know better than I. He served as the Deputy Mission System Engineer, Spacecraft Manager, and Deputy Observatory Manager at JWST. Currently, he's a Mission Systems Engineer supporting my office, the Goddard Newport News office. And prior to Goddard, he worked for Aerospace Corporation, Orbital Sciences, and Lockheed in various aerospace programs, including Lunar Prospector, Spitzer, Titan IV, Centaur, Athena, and Taurus launch vehicles. Richard, I'm going to hand it over to you to talk about the Venus flagship mission.
I turn my camera off, or my bandwidth will be very poor. All right, questions? No. How did I get to the end slide? Give me a second. All right. So this is the Venus flagship mission. Martha Gilmore is our PI, and Patricia Beauchamp from JPO is also our science lead. On behalf of the entire team, I am going to walk you through a very brief couple of charts on the overview, and then we'll dive into the lander, and if you have any questions. So the Venus flagship mission has 3 goals that we're trying to address, all associated with the habitability of Venus. The first is to understand the history of volatiles and liquid water on Venus and determine if Venus was habitable. Second is to understand the composition and climatological history of the surface of Venus and the present-day couplings between the surface and the atmosphere, and to understand the geologic history of Venus and whether Venus is active today. And the way we formulated the mission, it addresses the VEX-AG goals as well as goals from the 2020 NASA Science Plan, does that across both the Planetary Science Division, the Heliophysics Division, and even the Astrophysics Division in a few places. All right, we're building this mission upon the critical science that's enabled by multiple platforms. A lot of this was informed from the 2009-2010 decadal survey that was done, where they looked at a whole bunch of different platforms and how they might accomplish different sciences. So we're building on that, standing on the shoulder of giants, so to speak. And of course, there's this long history of Venera and Vega missions, and of course, Venera D is coming up in the future as well, that we're trying to learn from and build on. So the architecture we've come up with has 4 elements or platforms, depending on how you want to look at it. There's a orbiter, which actually serves as the carrier vehicle, and it's one of the enabling things we believe for this mission, is that the carrier is able to launch on a single launch vehicle and have everything arrive relatively around the same time. There's an aerobot, which is a fancy name for a balloon that will quote-unquote orbit the planet between 52 and 62 kilometers, which is a very nice zone. It's very mild compared to the rest of Venus. Then there's the lander. The lander has descent science on it, and we take about an hour to descend, and we're taking science during that hour. And then we survive on the surface for up to 7 hours. And then we have an additional payload we're carrying, which is a long-lived science explorer, Lizzie, and I think it's also slated for Venera D as well. And that one will operate for 60 days, taking atmospheric science mostly. And then we have a couple of small sats, which really are a key part of our architecture. They arrive actually before the orbiter does, about 3 months early, so that they can provide comm for the aerobot, which has a life of about 60 days. So they'll provide that comm. The orbiter with the lander attached will go into orbit. Orbiter has a radar, so we're able to do some mapping not a large percent, but some mapping of the landing site to help get us some better images. It has a 10-meter resolution. And then a year later, due to the way the orbit works around Venus, we'll be able to actually detach the lander and have it land. So we're fortunate that there's a lot of Venus science proposals and concepts being worked right now. Veritas, is in the discovery selection, and it could be a very good pathfinder for us, and could enable some cost savings. If the Vinci Plus mission is selected, it would help inform the descent profile and imaging of Tesla locations. Again, that data would help us understand our landing site better because we do intend to land on the Tesla. And so it would reduce risk and cost. If Envision proceeds, then it would be very timely, again, more radar imaging and emissivity data that we could use. And of course, Venera D is both synergistic and complementary because it's doing some of the same investigations as we are. All right, here's our timeline. We launch June 6th of 2031. A few hours after that, the small sats are separated and they begin their long journey to Venus using solar electric propulsion. The rest of the stack does a Venus flyby on October 13th of 31. And then we come back around November 4th of 2034 when we separate the aerobots. And of course, the small sats, as I mentioned earlier, they would have arrived in mid-August. So they're ready to capture the entry and the 60 days of aerobot mission. Then on November 9th, about 5 days later, the orbiter and the lander will do their Venus orbit insertion. Like I mentioned, there'll be some radar mapping as we do that. And then we'll continue on in a highly elliptical polar orbit where we will conduct science. And then we'll come back a year later to the entry location for the landing site we've chosen, which is about May 16th of 2035. 3 days later, the lander will land. It'll operate for 7 hours. Then the orbiter will then begin aerobraking phase that lasts between 2 and 4 years. Once it completes that phase, there will be an additional science phase and a circular polar orbit where the radar will map much to most of the surface, and our other science instruments will be able to get all the data they need as well. The mission elements, a little more data on them. On the left here, I show a trade tree of some of the trades we did for the architecture and the mission design that then drove our mission requirements on each of the elements. We also have a allocation of the measurements that we want to make for each platform, and I'll show you the list of the instruments that got assigned as a result to each platform. But we launch on a Falcon 9 Heavy expendable. As you can see there, the aerobot is tucked underneath in a custom payload adapter that we've designed. The lander is on top. The two small sats are on either side. They've got their folded up deployable 2.5 meter antennas on either side. You can see the UHF antenna for the orbiter. That's for talking with Lizzie. And then you can see 2 of the 4 4,000 Newton thrusters that perform all our burn maneuvers. And then over to the right is stowed the radar antenna, which also serves as this yeoman's duty. It does radar, does S-band comm to the lander and to the aerobots, and then it also does X-band and K-band to Earth. On the bottom here is the lander. I've got some more dimensions on another slide I'll show you. One of the key features that we are exploring are these what we call fans or propellers that we are using with the hazard avoidance system to provide a way to provide an impulse or a thrust in the Venus atmosphere. And I'll talk more about those in a minute. And then the aerobot over here, this is the shape it takes. It's actually got another balloon inside of it. And to rise and lower, it transfers the helium back and forth between the bigger outer balloon and the smaller inner balloon. This graphic is not the scale, because if it was, the aerobot itself would be, the gondola itself would be very small and hard to see. But this is our gondola, and then of course our two small stats are at the top. Our total launch mass, including almost 3,400 kilograms of propellant, is nearly 9,200 kilograms. The Falcon Heavy gives us a little over 11,600 kilograms of performance, and we do have about 27% mass margin. This is the list of the elements and the instruments that have been assigned to them in order to complete the desired science. As you can see, we've got quite a few on the lander, and the small sats have some as well. I'm not going to go through them in the interest of time, but this is here for your reference. On the lander, so this is the lander trade tree that we did. Did a lot of work trying to figure out what the lander should look like. We decided on 4 legs and a complementary requirement that the CG of the sphere be low in comparison. The idea is that we can get a much more stable base for landing on Tesla and on slopes that can get up to 30 degrees with a wide footprint of the legs than in a ring lander that's been done in the past. And those ring landers, when we looked at it, we thought we would need outriggers to prevent tipping or sliding. And so going with the legs, we believe does all that. There are some trades that we just didn't get to on the foot pad, whether that should be spiked or what other characteristics it might have to, again, assist in making sure there's no sliding once we land on a slope. You'll notice near the top there's a drag plate, kind of gives you an interior view of it. We use that during the descent to provide drag to lower us after we've gone off the parachute. I'll go through the descent sequence here in a couple of slides. But I wanted to give you a design of the lander first. And the aero shell, one of the things we did is we decided early on we wanted to try to limit the entry Gs. In the past, entry Gs could be in the hundreds of Gs. We set a goal for 50 G entry peak, and we were able to obtain that. It allowed us to use a 70-degree cone sphere aeroshell, which reduced our heating, which reduced the mass of cheek material that we needed. And so it had several different benefits. It allowed us also to get that wider leg stance out there, which is about 2.5 meters, 2.4 meters. And then inside the sphere, we have 2 decks that are filled with phase change material, and that phase change material is what primarily gives us our long life. Of course, we also have high temperature MOI and regular MOI spread throughout. We do have 3 windows, which I'll show you on the next page, in order to get some of our instruments and our hazard avoidance system to see out. We use a 3-pane sapphire glass assembly to do that. At the top of the lander is the, shown in the bottom picture here, is the S-band Omni antenna, and underneath that is our panoramic camera. It has 4 different mirrors that it can view to get about a 240-degree field of view around the lander. Here's some more on the layouts. I was just talking about the antenna and the Omni. This is where the nephelometer is. It's out on the balloon. The mass spectrometer has 2 ingestion ports where we ingest 2 samples. And one of the ways we do that is when we ingest, we have these 3 tanks shown here, or you kind of see them up in this other corner. They basically suck the inrushing Venus atmosphere into those tanks to prevent that from getting inside the sphere and eating up the sphere too much. And we have a mass spectrometer out and a tunable laser spectrometer as well. This is the top deck on the top, the upper portion. The lower portion of the top deck is shown here. We have all our batteries, our IMUs, many of our electronics are here. And then there's a nephelometer again on its boom. In the bottom left corner here, you can see the 3 viewports I was telling you about. There's a descent imager window, there's a hazard avoidance window for a LiDAR, and then there's a window for the Raman lens instrument. And the bottom deck on the upper side contains our CNVH, our mass spec, a couple of notional instruments. We changed the names of these recently, and I unfortunately can't remember what the new names are. But you can see our sample ingestion system here, and then on the bottom deck, some more electronics. Oh, I should have pointed that out. On the top deck in the right-hand corner here, there's a mounting point for the Lizzie instrument here. The lander doesn't provide any power or data. Only thing we provide to them is a place to mount. They're very much self-contained. They're about 10 kilograms their mass. It's very interesting. They're taking advantage of recent developments in high temperature sensors, and electronics, and comm system, as well as a battery that they've recently demonstrated that can survive the high temperatures. And then what they do is they take some low data volume measurements, mostly the atmospheric, as I mentioned, and then once a day for about 5 minutes, they use UHF comms to either the orbiter or the small sat to dump their data. You can see the measurements that are there. And the goal is for this to last at least 60 Earth days, which is about half a Venus day. And they want to try to cover that day-night transition. And we'll see. The other thing that was asked to do was show a comparison to the Venera Vega payloads. Several things are similar and some are different. We have descent imaging and they didn't. We are trying to land on Tessera and they landed on planes. That's what drove our decision about the legs versus their ring lander. They didn't have a way to control laterally. We think we found a concept to do that with our fans. Our legs do have crushable material. They also adjust when we land to accommodate the landing load. So if we come down and land on one leg, it doesn't break. We can handle that and land on all 4. And then they're also adjustable after landing, so that we can maintain the orientation of the drill and also try to keep the Omni antenna pointed to the sky. Just like the Venera, we're passive, and we believe we can get up to 8 hours of lifetime. Our landing sites are shown here. The number 1 landing site is West Ovda, which is shown here with this red circle of the number 1. Other sites are Alpha and Fortuna and Tellus, and then a couple Mid-Ova and East Ova. And of course, as I mentioned earlier, we're actually coming in to a circular orbit that's polar, or not circular, elliptical orbit that's polar. So we'll actually go over all these sites during that year that it takes. And if we decide that there's things we don't like about site 1, we can hit site 2 and site 3 and so forth. Safe landing. There's a picture there that shows what approximately a 30-degree slope looks like on Earth, and similar, we believe, to what we would see in the Tessera. Our goal, of course, is to land there safely and ingest our samples. We use gravity for our sample delivery. So again, it's important that we get level. Challenges are the uneven surface and the rocks and regolith or sediment material that we're going to be landing on. We're going to do a lot of work ahead of time on landing site analysis, try to understand the slopes and the types of material. And that's where earlier on I mentioned the other missions that could help inform us there. We do believe we need a hazard detection and avoidance system to reduce risk. Not required for the mission, but it does reduce risk. We'll need real-time processing of the descent images. We'll need a LiDAR, and we're in the middle of still looking at LiDAR systems. Goddard has one they're developing for Europa. and for the moon under a program which seems I forget the name of the program, but that we're developing. We also have some that we're developing for our Restore L program. So there's several different candidates there that might work. I'll show in the landing slide that we have to get below the clouds before we can use the LiDAR. So that means starting around 10 kilometers and down, which in our descent profile gives us about 16 minutes. And then we would use the fans to try to redirect the lander to avoid steep slopes or large boulders or unexpected hazards. I think I talked about the mechanisms on the legs already and the drill and the antenna. I'll move on to the next chart. So here's the landing sequence. We start off at 175 kilometers interfacing with the atmosphere. We'll be going about 10 kilometers per second at a very low entry angle. This is minus 8.5. Others have been up to 4 times that when they've come in. And the altitude rate will be decreasing at about 1.4 kilometers per second at that point. And our peak G, as I mentioned earlier, is 50 Gs. About 125 seconds in, we'll deploy the chute. That'll be at an altitude of about 75.3 kilometers. We'll be going Mach 1.4. The chute is about 10 meters in diameter, and our lander mass at that point is about 1,200 kilograms. About 230 seconds later, we'll drop the heat shield. That'll be around 60 kilometers, and we will have reduced our speed to Mach 0.7. About 30 seconds later, we'll reduce we'll separate from the back shell, and the back shell and the parachute will drift away, and the lander will be in free fall using the drag plates. At about 2,634 seconds, we should reach an altitude of 9 kilometers. That's when we believe we can do our first hazard avoidance measurement, and then we can use our fans. We estimate it takes about 300 seconds with our fans to impart a change in course. Right now, we had baselined 10 centimeter fans, and the estimates are we get about 5 meters of lateral change. We're looking at a couple things, increasing the power to them so that we can spin them faster, and doing that with the same 10 centimeter fans. We think we can get 50 meters of lateral distance, and we are also looking at 20 and 30 centimeter fans as well. Our second hazard avoidance opportunity is around 5 kilometers. Again, we'll take some measurements with the LiDAR and do three minutes or so of the fans until we touch down a little over an hour since the entry. And we land with an altitude rate of, or a landing velocity of 7.8 meters per second. We do think there could be up to 2 meters per second lateral winds, and again, we'll use the fans at that point to null out that lateral velocity. We do have an IMU on board, so we can measure the disturbances and know when we can apply those forces. I think you might be interested in the heat shield. It's a tiled single-layer heat material. It weighs about 214 kilograms, has a thickness of 0.6 inches. The peak heating is 1,734 watts per centimeter squared for a total load of 23,875 joules per centimeter squared. This material is the same as what's being used on the MSR entry vehicle. The back shell will stick with PICA. It's got a mass of 41 kilograms. Same has been used in several missions in the past and what's being used on Perseverance. The parachute is a disc gap band with a mass of around 35.6 kilograms. And our coefficient of drag area is required to be 7.63 meters squared in order to get the drag coefficient we need of 6.75. All right, so we made it to the surface. How do we get our lander lifetime? The sphere is painted white with a conductive coating. Before we begin our descent, the lander will be at minus 25 C, give us a good cold soak temperature for the internals. Temperature on the outside, of course, will rapidly increase as we enter the atmosphere. The phase change material we're using is designed to operate at 37C. It's a wax, iocane wax. That combined with our decks, we're able to flatten the temperature rate, and I'll go through that in a minute on the graphic at the bottom. We have the decks thermally isolated from the sphere with a titanium flexure ring. All the avionics and instruments are thermally coupled to 2 decks, as I showed you earlier. We have a low emissivity coating on the triple pane sapphire windows. It's got an emissivity of 0.15. Our sphere is evacuated to high vacuum conditions to help reduce the convective heat transfer and make the MLI blankets effective. We also use zeolite to keep high vacuum during the outgassing, during the cruise phase. MLI blanketing, we've had a high temperature as well as regular MLI on the inner walls of the sphere and standard Kapton on the decks. And then this bottom plot shows our instruments, when they'll be operating. In the middle, on the top, it shows our comm relay. So for the first few minutes, one of our small sats will be in contact during the entire descent in the first few minutes of landing. And then our orbiter takes over for 80 minutes. And then the small sats take over starting about 90 minutes in for the rest of the landing time. The orbiter can get 5 gigabits of data, which is actually the total amount we're expecting to get from all the instruments. It can get it down in 30 minutes. So we have quite a bit of margin on the link for the lander there. And our highest data rate instruments are, of course, the cameras. So those are early on and are covered by the orbiter. And then the other instruments that continue have much smaller data rates, and the small sats can capture that data as well. You'll see I've got a gradation of colors there. For the first 70 minutes or so, we'll be between 0 and 37 degrees, according to our thermal models. And then we'll start to heat up. We'll get into the 37C range, where our phase change material will take out all the heat. So we get a nice steady state for about 240 minutes or so until we get around the 6-hour mark. And then we will have exhausted our phase change material, and the temperature will rapidly increase. After about 7 hours, we'll be at 60 degrees C, and it will continue rapidly increasing after that. We were asked about mobility. You might have seen on one of the trade starts, trade trees early on in this presentation, that we didn't include a rover. And of course, that was based on a lot of that work from 2009 that I had mentioned the previous decadal study. So what we came up with was instruments that can provide mobility, in quotes, from inside the sphere, so that we can get a detailed characterization of the site we're at, and allow for instruments that can perform, analysis that might take longer than trying to move, and get a more complete data set. And of course, the Raman Libs gives us an opportunity to sample multiple locations up to about 2 meters from the lander. And it's got a fairly large field of view, 1,100 centimeters squared field of view. So we get a good characterization of the local landing environments. Most of the other instruments, of course, are fixed volume, and allows us to sample some different materials and soils and rock surfaces, as well as maybe individual minerals or class. So that's how we handled mobility without a rover. And that ends my tour. I know it was very quick. There's lots more I could tell you, but do you have any questions?
Thank you, Richard. We'll open it up for questions, and I'll kick us off with a prepared one here. Are there any measurements that would reduce the risk of landing, such as better radar images or even visible images, obtained from precursor descent missions?
Yeah, there are 2 major uncertainties, which I think I mentioned. We've got the slopes and the size of obstacle scarps, steep scarps there, and having more data, higher resolution data on those would absolutely help us plan in advance. And then, of course, We've got analogs from Mars that we can use and help us inform our algorithms and processing artificial intelligence, if you will, to detect what the hazard is in our hazard avoidance system.
Here's a question from Alex Hoffman. I'm no expert, but I believe low entry angles correspond to large uncertainty in landing location, probably exacerbated by winds acting on the parachute. Are the leg fans or another system able to ensure that you don't land many kilometers off course?
So our landing ellipse is 300 kilometers in the north-south direction and 150 in the east-west. Of course, the north-south is because of the entry angle and the velocity that we're coming in, of course. And then the east-west is what's driven by the wind. So yes, it can, and we're aware of that, and we have it. As I mentioned, we can't really use the hazard avoidance system until we're below the clouds. So we could very well drift in that landing ellipse. But once we get below the clouds and can see where we're at, and use some terrain navigation features, then we can move the vehicle, like I said, up to 50 meters right now is our best estimate.
Great. So I'll end us with one last question from Jeff Landis here. Fans are an inefficient way to change the trajectory of a descending object, as the vehicle carries the drag surface of many square meters. Only a trivial change in angle of attack would give you far more lateral mobility than propellers. So were any control surfaces considered on the drag plate?
We did consider that. We were concerned with the few things. We were concerned with having that large of a surface moving in the higher altitudes, and the heating that would go on with them, and the added mass that would be needed to make them aerodynamically structural. So the structural loads on them we thought would be high. And yes, the fans are not as efficient, but we explored other options. We thought about thrusters, but of course the high pressure on Venus makes those useless. You can't overcome them, overcome the pressure on the nozzles. We thought about having some kind of control moment wheel that you could change the orientation and help steer the vehicle. And again, that seemed very complex, took a lot of volume up, and didn't seem feasible. Whereas these fans, they do give us an ability to get some lateral distance change, and that could be enough. More work definitely is needed on these fans. They're very low TRL, I mean, it's just a concept, but I think there's some promise there.
All right, thank you, Richard. So with that, we'll move on to closing announcements. So I'd like to take a brief moment to remind our audience of our full-length article opportunity, which is taking place now, the interim between the two IPPW, or the previous IPPW conference and our next one planned in Japan. We have organized a new AAAA Journal of Spacecraft and Rockets virtual collection for this year titled Innovative Methods, Instruments, and Materials for Planetary Entry, and we're specifically looking for journal-quality full-length articles based off of your IPPW 2020 material. Articles will go through JSR peer review, and Carl Edquist of NASA Langley will be the associate editor in charge of this collection. The due date is September 11th, 2020, and the submission site is already live at Manuscript Central. More details can also be found on our IPPW webinar website. And with that, I'll hand it back to Jim for closing remarks.
Well, thank you, Jacob. This is Jim Cutts, and I want to thank everybody for this particular presentation, but also to point out that this has been the final session of the IPPW 2020 webinar series. And on behalf of the team that has put this program together, not only at JPL, but elsewhere in the US and Europe, I want to thank all of the presenters throughout the entire series, hosts and the moderators for their contributions. We hope it has, to some measure at least, mitigated the disappointment of not being able to gather in person this year in Monterey for the workshop. Perhaps it has also pioneered some new ways for our community to communicate in the future. In any case, we thank all of the attendees who have joined the series from across the globe, and we hope to see many of you next year when we convene in September in Tokyo for IPPW 2021.